Okay, guys, welcome to today's show. Before we start, I just want to mention that on this Friday, the 21st, I will have a live stream where we will create our very own in memory cache database, like Redis, but faster. That is the intention, anyway. And in anticipation of that live stream where we create a database, I will today create a data structure, a form of a binary tree, my own way of implementing it, which will be able to store data effectively. So that's what we're going to do today. And if you want to have more details about how the binary tree is constructed or designed, I recommend watching my last episode where I draw the tree graphically. But today it's all code, so let's begin by creating a directory for this project. Let's just call it tree, like so. And I'm gonna set the home directory to my current working directory, so it makes stuff a little bit easier. And as usual, I'm gonna use Sociopath SCP client in order to alter the files live on my Linux server. If you do this project at home and don't have an external server, that's no problem. Then you just do this locally as usual. So let's see, where did I put it? Inside the temporary directory and tree. So I right click and open in editor. And currently this is just an empty directory. Let me just position this a little bit. Let's see, something like this. And I'm gonna create the files. So we need a tree.h in order to keep all our definitions and stuff. And we need tree.c where we put the entire programming implementation. And I will also create a make file to make stuff a little bit easier to compile and recompile. And I'm going to use this same the same kind of make file as I usually do. So what do we have? We want to compile tree.o and we need tree.c for that. So we will run cc with possibly a couple of flags. And I'll make this a little bit smaller. I hope you don't have problem seeing this. And we're gonna do -c and the name of the input file, which this represents. Okay, and when we have tree.o, we can compile tree, which requires tree.o. And in order to do that, we run cc with our flags. And then we will do, let's see, we will take the target, and as output file we will have, we will take the source, and as output file we will have the target. So that's a symbol for the target, and possibly we will have some kind of LD flags for the linking process, like so. I will also create a clean, which will simply remove all the O files and the tree binary. And finally we will do all tree. Okay, so that's most of the makefile done. And I will just create those variables. So we have flags and we have LD flags. I will leave LD flags empty for now, but I want to compile this using WAll, and let's do O2 for optimization. And let's also define the standard to be C23 or C2X, because this release of GCC was released right before the C23 standard was released. So that's why they called it C2X, because they were not 100% sure if the feature list would have matched the C23 standard. So that's why. Alright, let's save our makefile. Let's save our tree.c, and let's save our H file. And hopefully they have been uploaded. They have not. No, I was disconnected from the server. Let's reconnect. That's a good thing with Sociopath, by the way. Even if you have a lot of files open, if you get disconnected and just reconnect, then you should be able to just save again. And let's see, we save this, we save this, and we save this. There they are. So let's do make. Okay, I need to do double of this, I think. std, oh no, it should be std equals. There we go. So the only error now is that the file is empty. So let's remedy that. I will simply create an empty main, and let's do hello world, like so. We return 0, and we include std, no, not here. Let's include our own tree.h instead. We save this one, and inside of tree.h we put all these regular header includes. Okay, and if we just do make, we have ourselves a binary. Hello world. Okay, so that's structuring our project. I will add a couple of more includes. I have 4, which I almost always use in every project. I'm not 100% sure I'm gonna need all of these, but let's prune them off at the end instead. so we don't have to go back here just to include stuff. And let's also include some error thingies. So I want assert, and I also want error number. And in order for them to work properly, I do also need to define GNU source, like so. Okay, so that's a little bit structuring. Now to our real project. So I want to create this kind of binary tree that I showed in the last episode. So basically we will have a, let's see, a couple of nodes. So first we have the slash, for example. In the next level we have another folder such that users perhaps, and then we might have users slash login or something like that, and this grows like nodes in a tree. So we can have basically how many of these as we want. The only limiting factor will be the variable that we store this string inside. When I experimented a little bit on my own, I created a system that only saves this part, so not the slashes. And in this level we only save users, and in this level we save users and login. But I don't think I'm gonna do it that way this time, because what I want to create is a very fast structure based on CPU speed. I don't care if we waste a little memory, as long as it's not extremely inefficient. So if we keep copies of the whole string on each level, it might add a couple of kilobytes at most, and it will make our parsing a lot of easier. So I'll do that. And each of these folders, or nodes as I call them, can contain one or more values. So we might have, for instance, let's say we have users Jonas, we have users Jim, and so on. And those are the leaves. So this will contain a value, for example, and Jim will contain a value. And these needs to be unique in the folder, but we can have a Jonas inside of login as well if we like. So this creates linked lists from these nodes. So basically it's a couple of linked lists, one per folder, each including the value. And then we have the binary tree consisting of this folder structure. Okay, that's a lot of information at once. So how do we begin? It's a rather, what should I say? It's a rather ambitious project, creating this binary tree and make it efficient. So where do we start in a project like that? I like to start with the types. So I will have a type which is called node and one that is leaf. And those two together, they form a tree. So a tree can be one of two things. It can be either a node or a leaf. And these are structures containing values in the case of leaf, and just links to other levels in the case of the node. Alright, so let's start there. I'm gonna create a structure which I will call S node. S is how I name my structures. And what do we need for a node? Well, if we think about the links, there is an uplink to the layer above us, and that is always a node because only nodes can connect to other structures of the tree. So this is an struct S node, and it goes upwards. And if we are at the top, at the root, then this up will point to itself. It will point to this node. Otherwise, it will point to the node on the layer above. What else do we have? We might have a link to the left, downwards to the left. Let's call this left. Or perhaps we shouldn't use left and right and up, but perhaps we should use the cardinal directions instead. That looks a little bit more precise. So let's call this north and this west. It's west, right? West. Yeah. And we will also have a link to the right, but that's not a node, that's a leaf, because to the right or to the east we're gonna link to the first leaf in that arm that goes to the right. Okay, so there we have our links. We do also need to save our path. And I could make this a char, but I don't like that. I want to create my own, a little bit more precise types or integers. Let's do a type def, and I want to have a 32-bit int. So that is, in my case, an unsigned int, and I'll call that int32. I will also have a 16-bit int, and that is an unsigned short int, and I will call it int16. And finally I want the 8-bit int, and that is simply an unsigned char. So int8, and the int8 is the one that I'm going to use here, right here. So int8, and let's call it path, and let's do it like this, as an array of 256 bytes. So this will contain the whole path, not just the current level. And what else? We're not going to have any level, we're not going to have any values. So that's nothing to think about. Perhaps we should do this as an U tree instead, because we don't know if, I think I will make the root a little bit different, so it's a node but it's not a node, and perhaps we need to do this. Let's have it like this for the time being, and we'll give it more thought when we need to. Okay, and we need to give this a name. So type def struct s node, and I want to call it node with a capital N, like so. Okay, so the most of the node is done. Now we need to create our leaf. So struct s leaf, And what will a leaf contain? If we begin with the connections, it will have a northern connection, right? Or rather, it will have a western connection to the leaf on the left, or to the node if it's the first one. So I think I will go back here to, let's do an S node here, but here we will do a tree instead. So struct, no, not struct, it's a union, and I'm going to talk a little bit more about unions later on. So union U tree, and this will go to the west. And perhaps we will have a link to the right as well if there are more values. So it will be a struct S leaf, and it goes to the east. Okay, that's the two links. We will also have a path. So, and I don't think I'm gonna call this a path. No, let's call this a key, because it will be like a key in a regular object type data structure, which this kinda is. And let's say a key is 128 bytes. And we will also have a value, but the value I will not store inside of here. I will just do a pointer to the value. So we will allocate that separately and just point to that value, because the key can be rather small, right? But the value can be rather large. Perhaps we have a big JSON structure here inside of this or something. And it can also be a lot less than 128. So by doing it this way, we can add, let's say, a 16-bit count, or perhaps size. And that is the size of this value. Okay? So yeah, that's basically it. And we will give this a name as well. So type def struct s leaf, and leaf with a capital L, like so. And finally we will create a tree structure, and that's a union. So it'll be union U tree. And what will the union contain? Well, it can contain one of two things. Either it's a node N, or it's a leaf L. And that's the thing about unions. All the different variables in the unions share the same memory space, which means I can only have one node or one leaf, not both at the same time. But in a structure, we can have everything at the same time. So let's give this a name as well. So type def union U tree, and we will call it tree like this. Okay, so let's create one of those structures. I'm going to create functions that do that, but the root of the tree I'm gonna initialize using the new tools for that in the latest C release. So I can do something like tree root equals and these curly brackets, and I need to have the definition of the node. By the way, I forgot something. I do also want to have a tag. So tag, and same for the node. So tag. And what is a tag? Well, it's a type def unsigned char tag. And it can be one out of at least two things. So define tag, or three things, by the way. It can be a root. Let's say we have 1, and I usually put the binary representation as well. And we can have a node, a tag node, which will be 2, and that is 0, 0, 0, 0, 1, 0. And we can also have a tag leaf, which will be number 4, and that's 0, 1, 0, 0. And if you look at this 1, it goes to the left every time, which makes it possible to have one of these or several of these in the same variable. So this is how we is able to, if we look for a tree, for example, then we have the possibility of looking at this tag to figure out at runtime what kind of structure this is. Okay? And let's copy this into a comment so I can, or maybe we can, no, let's copy it to the comment. I think the screen is a little bit too small for split screens and stuff. Okay. So let's define a root, and we have a couple of different things here. We will have a tag, so we do dot tag equals. It's as simple as that. And what will we have here? Well, we want to have the tag root, but we do also want to have the tag node, because the root is a node after all. So let's do an or sign right here and do tag leaf. No, tag node. So this can be either a root, or it can be a root and a node at the same time. Okay, that's tag. Then we have north, and north will simply, let's cast this to a tree and point towards itself. So we know if it points to itself, then we know it's the root. Then we have west, and west we will just initialize to 0. Same with the east. Do we have an east? No. Yeah, we do. So east equals 0, and path equals slash, like so. And then we have the tree defined, without having to do it inside of a function or anything. Kinda neat. And let's, for instance, print out the address. Let's do %p for pointer, and then we will just think we can just say root here. Let's try it out. And let's change one thing in the make file, by the way. So where were we? Right here. I want the standard make command to compile the tree, but first do a clean. Like so. Let's see what it says. Okay, that's a couple of warnings. Probably one of these that creates the rest. Let's see. Type def union u3 expected blah 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 before union. Oh, I misspelled type def. So let's see. This should be in the .h. I want to have this in the on the right. Let's see, where is it? Okay, this shouldn't be here either. Type def, like so. And now probably most of the warnings will have disappeared. No? Let's see. Tree has no member named tag. Ah, right. It's a little bit trickier when we have a union like that, because you see these, we need to specify the N or the L as well. So how to do that? What if we were to just do .n equals, and then we have a double of this? Will that work? Okay, that's better. Initiation of struct as node from incompatible pointer type tree. Right, we shouldn't typecast it to tree. It is a tree. We should typecast it to a node. So let's see. This far it has been very easy things to fix. Like so. And let's try it again. Okay, one thing left. Warning, format expects argument of type for star, but it's a tree. Okay, we need to typecast again. A lot of typecast in this project. And this will be it will be a void like this, I think. Cannot convert to a pointer type. Well, let's do it by reference instead. There we go. And there it is. It compiled. And it runs. Okay, so now that we have defined our data structures, let's create a utility function which creates and links up one of these trees. So let's call it, I don't know, create node. And what kind of arguments do we need? Well, we need to know the parent. So let's create one of these arguments like this. And we do also need the path. So that will be an int8 pointer. And we just call it path, like so. And in order to know, let's see, well, we can do something like this. Assert that the parent is there, so it's not null. Let's create a pointer for the node, and let's see, we will need something with a size as well, I think. So the size variable, we can reuse that to work with the path as well, if we need to. Okay, so let's see. We need to allocate memory for this one first. So let's set n equal to, and it's going to be a node malloc size. So let's set the size to size of struct s node. And then we will zero out that structure. So let's do something like int8 and the n and the size. And we need to create this zero function as well. So the zero function will be a void function. No need to return anything. But we do need two arguments. And let the first be an int8 pointer. Let's call this the... it would mostly be used for strings, so let's call it str. And then we will have an int16 size as well. And we will simply loop through this string and zero everything out. So basically like the mem set, but I want to avoid using any library functions if I can. And this is a rather simple function to write, so let's also create a int16n. Let's initialize n to 0, and p will point towards str. And we're going to loop as soon as p dereferenced is not null. And then we'll just increase p and we'll increase n. So we will also, no, let's remove this, by the way. Instead, we will check if n is less than size. That's better. Okay, and for each step of the way, we will simply set p to 0 and then return. Okay, so we have created our structure, we have zeroed it out. What's next? Now we need to link it up. And we have the parent specified. So we'll simply do parent, and let's see, this will be the west. So let's set this to n. So the parent's left leg will be pointing towards this new structure, and then we will initialize the fields inside of n as well. So let's see what we've got. Here is the node. I think I'm gonna copy this into a comment, make stuff a little bit easier. So let's see, we'll set the tag to tag node, and we will set north to the parent. What else do we have? We have the east, which will be 0, and then we have the path. So let's do a simple string copy, and we will need to create cast this to char, and this will be n path. And what will we copy there? It will be the path, and the size will be 255 at most. And that's it, I think. Let's just return n. So we have the tag, the uplink, the downlink, the link to the leaves, and the path. That's everything. Like so. So let's create one of these nodes and see if we can make that work. So let's create one of these pointers, and n will be equal to create node, and the first will be the parent, so let's say root, and the second, perhaps we need to reference it like this, and the second will be the path. So let's say we call this users. We assert that n is true. Let's create an n2. And n2 will be equal to create node, and this time we will set n as the parent, and the complete path will be users login. We'll stick with the same example, and let's assert n2 as well, and then we can perhaps print the addresses of these pointers. So %p, %p, and the first is n, the second is n2, like so, and then we will free n2 and we'll free n and return 0. Let me just check through this create node function if there is anything else we need to cast. So let's see, size of n equals malloc. This size perhaps need to be a regular int. 0 ought to be okay. And yeah, looks fine. I probably forgot about something, but let's go. Oh. Let's see. Create node passing argument 1 from incompatible pointer type, expected node star, but argument is of type tree star. That's right. We need to cast the north link as a tree. So let's just do that. Let's see, north. So this will be a tree because we're not. No, that can't be it. Which one was it? Here we go. Create node. Okay. Expected node. Right. Alright. So it's this one. Let's cast this to a node because the root is also a node. And one error should be gone. Yes. Create node user. Okay, it defaults to a char string. So let's cast this to an int 8. This is the trouble when you are using your own variable types, but I think that it has a lot of positive effects as well. Besides, you become really good at casting after a while. Now it compiled. Let's see. And we have 2 pointers and no error. It works perfectly fine. Nice. Okay, what's next? We can create our nodes. Perhaps we should create leaves then. Why not? So let's just create a leaf star. Create leaf. And what arguments do we need for this one? We will need a path. Or do we? We will need a key though. And we will also need a size to that key. What else? The path is included in the key, so that's nothing to worry about. We do, however, need to know the parent. So let's put the parent here as well. And that should be it, I think. Okay, so we need a node N. We need a leaf L, and no, we don't need the N. We do have the parent, so that's not really necessary. However, I want to assert that we do have a parent which is not 0. We need a key and a size. Right. Well, let's begin coding and see where it takes us. Okay, so we have the parent, so we know where the nearest node is, but it's not certain that this leaf is connected directly to its node. Perhaps there's a couple of different leaves between. So instead of creating a parent like this, I think we will have a tree, which can be a node or leaf, and this will be on the western side of this leaf. Okay, so let's assert the west instead. And it doesn't really matter to us if that is a node or a tree. So let's create, I will create a variable for this. I'm not sure I'm going to need it. But what do we need to do? We need to be able to find the last leaf. That's a good solution, because it will look something like this. We will have a node, and then we'll have leaf 1, then we'll have leaf 2, leaf 3, and so on. So we need to find the last leaf in the chain, and if we don't find any leaf, we will connect it directly to the node. That's a good solution, I think. Okay, so let's create that utility function. So this will return a leaf, and let's call it, let's see, find last. And do we need to give anything? Well, we need to give a parent, or the nearest node. Let's call it parent. So node parent. Right. So let's assert that we have a parent, and we need a leaf L, and we need a loop looking through this chain. Perhaps we should name this find last linear, because then we can optimize it later on and have like a find last something else, and then we can just alias that through a macro. So something like this: define find last x as find last linear x, and then we can simply change this one, and we don't need to change every function that calls that function. That's a good tip. Alright, so let's do a for loop. We point L towards the let's see, towards the east of the node. So the parent east, and we will loop as long as we have an L. So let's see, when L is 0, we stop. So it's better to loop as long as L have an east. And for each step, we will set L equal to L east. So one step to the right each iteration. But this will break if we don't have any leaves. So let's check that first. So if parent east is 0, then we will simply return 0. So let's have a function for that, or a macro rather. So we don't need those, and we can just say return error, no error. And then we define a macro for that. I like macros. Define return error of x. And what do we want to do then? We are going to find the backslash somewhere. Here it is. Okay, so let's do two things. Let's change the error number to x, and then we will return, let's return a null pointer. And what is a null pointer? Thinking, do we need to define that? That should be included in C23, but I'm not really sure that they did that properly, because that should be well, an object or a variable which always should be available. There is an include file called std something, std, let's see. So grep ri null pointer user include, and x86 something. There. Basic file. Type def, decal type, null pointer t, C++. Perhaps this is an older GCC or something. Never mind, let's do it another way. Oh, I shouldn't have closed that window. Where were I? Here, export home equals $pvd, $pvd, like that. And let's create our own null pointer. pointer instead. So let's see. Type def null point. Type def void star null pointer and null pointer equals 0. That should do it, right? Right, return null pointer. Now we can simply do ret no error. Let's also set this to 0 at the beginning in case some library call alters it. Let's do the same here. Our number equals no error. And nothing can really go wrong here unless we supply the wrong arguments. Okay, where were we? Find last linear. We want to find the last in the chain. So for each step we don't really need to do anything. As soon as there's nothing to the east, we will break out of this loop, and then L will simply be equal to the last one. We can, however, assert, no we can, yes we can, we really do that. Let's assert that L is not 0, and then we will simply return L. Okay, so now we have a utility function that will find the last node. So let's set L equal to find last. And what do we need for it? We need the parent. So how do we find the parent? We do not have that. Tree to the west. That could be a leaf as well, right? Perhaps we should do something like node parent, or possibly grandparent. Okay, so we have the parent, the nearest node, and that's all we need, right? Yeah. Okay, so find last, and we give the parent. Then we need to assert that we have a parent. And then we don't need to assert that we have west, because, let's see, no. Okay, so L is equal to find last parent. So after this line we have defined the nearest no, this is the last leaf, right? So if this returns 0, then we know we are directly connected to the right. let's just do this for now. Directly connected, and else L is a leaf. Alright, so before we do these checks, let's create this leaf. So we need another of these variables. Let's call this new, or new perhaps with an L. And let's create one for the size as well. But we have a size variable already. Let's call this count instead. That's more accurate. And this will be a size. And size will be equal to the size of a leaf. Struct s leaf. And new will be equal to a leaf casted malloc of size. And we assert that we have this new one. And now we come to this part. So if we are directly connected to our node, then we will simply do parent east equals new. And if we're not, then we will do L, let's see, no, this is to the right. So the east, yeah, that's right, by the way. So L east equals new, like so. And now we will simply initialize the fields of the leaf. As before, I will make a comment and paste this in, because with this font size my screen isn't big enough to split. I am aware of that function though. Okay, so before we do that, by the way, let's zero out this structure. So zero out an int 8 version of new size. And the rest of the fields, let's fill them in one at a time. So we have new tag equal to tag leaf. We have a tree to the west. So new west is equal to, depending on if we did this already, right? New, no, we did the other direction. Okay. So if we don't have an L, which means we're directly connected to the node, so then we will do something like this. It will be a node of the parent. Otherwise it will be a leaf of L, like so. And this is a ternary, kind of an if statement. Okay, what's next? New, and we have done tag, west, east. Then we have the key. Let's simply string copy the key. So let's make this a char, and we will use our key, this one. And we will copy, to the key, we copy our key. And how big is it? Let's do 127, so we have a little extra space, like so. And then we come to this part. So we will also have a value. So int 8 value. Like that. And let's reuse our size variable. So let's set size to the string length. No, let's not, by the way. We have a size as an argument, this count variable. We can use that instead. So what do we need to do? We need to create, let's select this, new value equals int 8 casted malloc of count bytes with 0 new value count times, and then we will, let's see, we will simply string copy cast to char, and it should go to new value. Perhaps we should assert that new value was able to allocate those bytes. So new.value, and the source is also char casted, and it's named value, and how big that will be count. Okay, so what do we have? We have the tag, we have the west, we have the east, key, value, size is left. So new size equals count. Return L. And it is linked up and ready. Okay, so now we should be able to create a leaf as well. Let's see if we can do that. Before that, let's just see if it compiles. Probably have a couple of errors. It's kind of impossible not to have when doing this semi-advanced piece of code. But it should be fast enough to resolve. Expected identifier, null pointer, return, before return, so 21. This is here. Let's remove this comment. And that changed the lines, of course. Let's run this again. It's still on line 21 in 3. Okay, in the H file. Do I have a yeah, I do. Okay. Line 21. Right. When we define a macro, we should end all the lines but the last one with this. And we should not have a semicolon. Alright. I hope the rest of the errors is as easy. Create node, error, no error undeclared. That's right, I did never declare those errors. And as of now, we do only have one. So define no error as 0. Like so. And size 16, that's not right. 59. 59 in the other file. 59. Right. This should be a int 16, of course. And the warning pointer type mismatch. Node parent. Pointer type mismatch in conditional expression. Cast a pointer from integer. Okay, that's another error. Let's see where we had this. Okay, new west equals node parent. And parent is node. Yeah, we should probably, let's see, where were we? Here. We should do the other way around. This should be tree, and this as well. Okay, warning, cast a pointer from integer of different size. The string copy char new value, char value, strncpy. Cast a pointer from integer. How did I declare this? Int 8 value, no? Yeah, it should be a star here, okay. This should be an int 8 pointer. And new size equals count L value required as left operand of the assignment. Oh, I forgot one letter. Let's see, where were we? Find last linear, create leaf, and new arrow size. Node star n warning unused variable. Okay, 58. 58. There. Let's remove that one. And now it should compile. There we go. Great. So the troubleshooting has been very smooth and effective today. I like that. Less than 5 minutes per session, I think. Finding this editor, on the other hand. Okay, let's see. Let's test this out then. We have 2 nodes, so let's connect something. Leaf L1, L2, and L1 equal to create leaf, and I don't remember we need a parent, we need a key, a value, and a count. Okay. So parent we have key, so int 8 key and value, and we need the size as well, so int 16 size. So before we create it, let's initialize those variables. Let's say we have a key of, so we're inside /user/login, perhaps it's my user, and the value might be, let's cast this by the way to an int 8, and same here. And what should be the value? Let's just put something, some kind of hex string or something. This could be like a session cookie variable or something like that. And the size will be equal to an int 16 of string length. And what do we send? We send the char version of value. Okay, so now we create a leaf and we connect it to M2, and we need the key and the value and the size. Like so. Let's assert we have an L1. And if we do, let's print something from that L1. For example, let's just print its value. So L1 value. And let's see if, let's begin there, by the way. What did it say? Unused variable. Okay, never mind that. And let's run tree. Assertion L1 failed. Why is that? That means that this create leaf failed. Assert parent. We have a parent. find last. New equals assert new. Turn L. $103, that's probably down in the main. Assert L1. We should have an L1. If we didn't have an L1, this function's assertions would fail, right? What are we returning? Return the L. And what is the L? Ah, right. We should not return the L. We should return the new. Of course. This is why these assertions are so necessary. Okay, this time it went through, and as you can see, we printed out the value inside of the leaf. But are we able to create another leaf hooked up to the first leaf? That's another story. So how do we do that? Let's reuse some variables. I will create another key. Let's call this John. And we will have a value, which simply will be another string, like so. And the size will be an int 16 version of the string length of the char version of value, like so. And L2 will be equal to create leaf, and this time let's see, we will still reference the nearest node right here, and it will find the last leaf. So key value size, we assert L2, and if it's non-negative we will print. Let's do the key this time. So the key of L2. Let's compile. What does it say? Warning, pointer, target, and assignment. Right, I forgot to do those. So int 8 and int 8. There we go. And let's see. We get John, we get this, and no error. So everything we have coded today has worked very fine. This is as long as we can go on in this episode. It's probably a lot more than an hour anyway. If you like this episode, there will be more in this series, and I hope you can like and subscribe to the channel. And on Friday I will have a live stream where I code the networking part of the main database program in C. So if you like this one, you will like the live stream even more. I see you Friday. Thanks for watching, and thanks for today.